Hi, welcome to another episode of Dr. Erin Explains the Universe. In this one, we're going to be talking about something from Star Trek Discovery. So if you're avoiding spoilers, I'm going to be talking about the mid-season finale of season 1. So get out now. Okay, you better be gone. All right. So we're going to be talking about the science of how they detect the cloaked Klingon vessels in this episode. Now we have triangulation and we have gravitational lensing, and the science is amazing. I was so happy to see this. I freaked out. Yeah. So in order to talk about this, we need to talk about two scientific principles. The first being triangulation and the second being gravitational lensing in order to explain all of this. So triangulation, what is it? Well, we use it a lot when it comes to being able to locate things, being able to map things, detect signals from somewhere, figure out where things are coming from. We use it all the time in the real world. Essentially what you're doing is, imagine you're trying to detect something, let's say on the ground. You just have, we're not talking about looking, we're talking about detecting maybe electromagnetic radiation. So maybe a radio signal. And you're looking for this radio signal and you're able to isolate it, but when you're only looking in one direction, you can only really isolate it to one strip of confidence. You can't narrow it down with just one thing looking in a direction, trying to figure out where this signal is coming from. What you do is you get this strip of confidence and then you move to another direction and you try to detect the signal again. Now what's going to happen is you're going to get another strip of confidence and those are going to cross. And where they cross, that'll give you a region where we think the signal may be coming from. We've also done this in the past with mapping. Now, this goes back way to like the 1800s and explorers, and they're trying to map out islands or anything like that. What they're doing is they look in one direction and they map it all out, and then they go to another direction and they map out what they're seeing there, and the combination of these, they're able to get a more accurate map of the land. It means you need to observe from at least two different directions, make a triangle, in order to isolate the location of something, or to map out a location of something. So triangulation, pretty straightforward, been around for a long time, just playing with geometry, trying to figure out how to map or locate objects. So all great, all well and good, but what if the thing you're trying to locate doesn't give off any signals that we're used to? A cloaked Klingon vessel, for example. Well, the thing that they come up with is trying to find the gravitational signature of this Klingon vessel. This is awesome. This is objectively awesome because it's essentially our issue that we have with dark matter right now. Scientists are able to see this mass of something, but it's not giving off any energy. All we see is the gravitational bending that's being caused by whatever is there, and that's what we call dark matter. So in my world, dark matter is essentially a Klingon vessel, cloaked Klingon vessel. We'll go with that. Okay. But what am I talking about? When we talk about gravitational lensing or gravitational field that's surrounding an object, what happens is, if you go back to my video on space-time, if you don't remember it or haven't seen it or have maybe not heard this concept before, space-time is this trampoline of our 3 dimensions plus time is a 4th dimension. And when you have mass, you bend this space-time, you curve this space-time around you like putting a bowling ball on a trampoline. Now you can imagine if you flick a marble toward that bowling ball, it's going to curve around. So you can imagine light does the same thing when it interacts or when it passes by an object in the universe that's bending space-time. So we actually see this. Light from stars get bent around our own sun before they come and reach us. And it was one of the first tests of Einstein's general relativity was to see if this actually happened. Lo and behold, they used an eclipse and they were able to see it. So when the eclipse happened, you could really pinpoint the stars that were coming from right behind the sun, and they were in a different position because their light was getting curved around the sun. So that's what we call gravitational lensing. This is what happens when you get light that gets bent around this massive bowling ball on a trampoline. So pretty cool. Science is pretty solid with this. We now see this also on huge macro scales, again, when we're trying to detect dark matter. What we do is we look at galaxies, we look at huge light coming from huge objects very far away, and that light gets bent or curved when it's coming past maybe a huge galaxy cluster or just a huge galaxy itself. We see light getting curved around it. But gravitational lensing is a really good way to map out matter in our universe. It allows us to sort of see the distribution of matter just by seeing how things are curved around. We also see, you may have heard of the term Einstein's Cross, and all this is just if you have a star that's directly behind another object, so you have a star back there and an object here, and you're looking right at it, if it's perfectly aligned, what's going to happen is the light gets curved this way, and this way, and this way, and you actually get 4 points. Now, if it's perfectly aligned, 100%, you'd actually get a perfect circle because the light would get curved in all the directions, but that rarely happens. If it's just slightly off axis, then you get 4 points, which we call an Einstein Cross. Here's a couple examples. I think you can see sort of an Einstein Cross here, and you can see galaxies getting curved around a big gravitational lens, a big galaxy cluster that we've seen with the Hubble telescope. So lots of cool examples. We see this all the time. So why hasn't this been used to detect Klingon ships in the past? Well, one of the problems that we have when it comes to mapping things is space is really big. And on a big scale that we're at, we are only in one position. We can only look around us and see where things are. Now, if we want to map it out perfectly, in an ideal world, we would sort of look at a cluster that we're maybe seeing some dark matter and we're seeing a big galaxy cluster, and then we would move to the other side of it and look at all of that over there and get a better map for what it actually looks like. We can't do that because space is really big and that would require a ton of travel time that we just don't have. So everything that we've done in space for this sort of technology, we've just looked in whatever directions that we can from here, and we've mapped out whatever gravitational lenses that we see from our position on a big scale, because that's all that we're technologically capable of. But thanks to Star Trek and future technologies, they play around with that idea a little more. So you have a ship that can jump, and so what they're going to do is they're going to jump all around this space where they think there's something, and they're going to look at the micro tiny gravitational lensing that happens in this space. So the idea is the ship is going to be here, Discovery's here, looking at empty space where we think there's a Klingon ship, and we're going to map out all the stars and everything that we see, and then we're going to move here. And we're going to look in that space, in that direction. We're going to map out all the stars that we see. And some of the stars' positions may have changed. So they're being bent around this point in space. But that doesn't give us a ton of information. So we're going to move again. And we're going to detect all these stars again from this direction, little ones in the different field of view. And we're going to see some of those have changed. So we map out this empty space using gravitational lensing and triangulation in order to map out what is possibly there distorting space-time. So they mapped out how many jumps would be required in order to fully map out this 3D ship that they need, and they know what a Klingon vessel looks like, and they say it's 133 micro jumps. Now, I haven't taken the time to figure out if that is actually accurate, but the science behind doing these micro jumps, as it were, and triangulating all of the different positions and looking at how the stars are bent in all the different directions, you could absolutely detect a cloaked Klingon vessel that way. This is how we're detecting dark matter, but we're not able to triangulate it, and we're only able to observe huge scale models of dark matter, huge scale examples. We're not able to detect kind of micro levels just because our technology isn't good enough. But Starfleet technology is. So this episode was awesome. This explanation for how to detect cloaked Klingon ships is awesome. Gravitational lensing and triangulation on a micro scale, 100% behind. I hope you followed along. Hit me up if you have any questions at Dr. Erin Mack on Twitter and Twitch. And I'm always happy to talk this. obviously super excited. Thanks for watching, and I will catch you next time.